So angular momentum is a property that is a lot like energy or mass or momentum, where it is always conserved regardless of what's going on. So first up, we've got a law of conservation of angular momentum. Angular momentum cannot be created, cannot be destroyed, but may be transferred. Law of conservation of angular momentum. Angular momentum cannot be created or destroyed, but may be transferred. That means that for a system of objects, we find that the sum of the angular momentums initially must be equal to the sum of the angular momentums finally. And yes, we're using L for angular momentum. No, I don't know why. Okay, so another way to write this would be L1 initial plus L2 initial plus L3 initial, etc. would be equal to L1 final plus L2 final plus L3 final, etc. Individually, an angular momentum is calculated as I omega, or the object's rotational inertia times its angular velocity. Now we're starting to be able to actually piece together the answer to the daily question, because we recognize that r, radius, directly impacts an object's I, rotational inertia. As this value decreases, we must see an increase in angular velocity so that we can hold this law of conservation of angular momentum to be a truthful statement. Let's see here. Units. Rotational inertia is kilogram meters squared. Angular velocity is radians per second. So what we see for units then is a kilogram meters squared per second, because technically a radian is a unitless value. Okay. All right. So that is equal to a change in angular momentum, or torque times T is equal to I delta omega, depending on which object is changed. Comet. So let's see here. Example. Well, I said a comet, so let's take a comet that's pretty common. Appears once every, I think it's like 74 years or something. Halley's Comet. So Halley's Comet, on its closest approach, comes within 1 AU, or sorry, 0.6 AU of the sun. Anybody know what an AU is? And I don't mean, hey, you, come over here. What'd you say it was? Astronomical unit. Yep. Astronomical unit. And an astronomical unit is the average distance of the Earth to the sun. So we are currently 1 AU away from the sun. Okay? Easy enough to do, because we just like to make everything in terms of us, because we're, egotistical like that. So 1 AU is the Earth to the sun distance. So at its closest approach, Halley's Comet is 0.6 AU. At its furthest approach, or furthest regression, I suppose, it's 35 AU, which is about the distance Pluto is from the sun. It actually goes out into the Kuiper belt, and that's where most comets are from. So this ranges from Pluto to just outside Mercury. When it's out in the Kuiper belt, Halley's Comet goes about 1 kilometer per second. These are all the actual values, because I, for some reason, happen to know them. So we can, using conservation of angular momentum, figure out how fast it's moving when it gets into the interior solar system. So to do that, we simply say the L initial is equal to the L final. L is I omega. And for a point mass, I is mr squared. Two, two, one, one. For the purpose of this problem, we'll say that Halley's Comet loses negligible mass. It does lose a little bit every time it goes or comes in due to melting, but then it regains some due to freezing as it goes back out. So we're getting rid of these masses. We're going to say they're equivalent. So here I have 0.6, here I have 35, but this is what kind of velocity? Linear, not angular. Okay, so I need to change this into an angular velocity. Well, or I could change my equation. Omega times r is equal to v, correct? So if I divide this by r, I can say omega is equal to v over r, and I can make that substitution. So now I have r squared v over r is equal to r2 squared v2 over r2. Cancel out these squares, and I've got a nice, easy relationship here where it's really just a ratio. R1 V1 is equal to R2 V2, not R2 D2, but V2. So I have 0.6 times V1 is equal to 35 times 1. Doing the math from here, divided by 0.6, 35 divided by 0.6, I get about 58 kilometers per second. So we can find the velocity of a comet going around the sun simply based on conservation of angular momentum. We can do the same with any object that would be counted as a satellite, whether that be a man-made satellite. We can do this with the moon going around Earth. We could do this with any planet going around the sun, because none of them are technically a circle. So everything speeds up and slows down according to conservation of angular momentum. Earth is very close to being a circle in terms of its orbit around the sun, but if you want to be picky, it's not. Questions about this example problem? Okay, I want to do one more then. So rather than just having a body that's moving around here, I want to do a rotational motion one. Well, really, this is more of a complex one, I suppose. So example 2. This is going to be a merry-go-round, or a, I can't think of what else you would call it other than a merry-go-round. Say again? No, because carousel's the big motorized one. I'm thinking the little playground toy that they are removing all over the place because they're dangerous and kids get stuck underneath them. You know. Do you know which toys I'm talking about? I have no idea, but they'll try to claim people have and that they're dangerous. So a merry-go-round we can approximate as a disc. It's got a large flat base and the handlebars are evenly distributed throughout the disc. So we're going to say that the merry-go-round has a mass of 200 kilograms, a radius of 2 meters. Okay, and we're going to take a kid and we're going to set a kid on the very outside of the merry-go-round. What's up, Connor? Oh, geez. Yep. All right. So mass of 200 kilograms, radius of 2 meters. Beyond that, we're going to put a kid, mass, let's go 94 kilograms, sits at the edge. While the merry-go-round is rotating once per second. How fast will the merry-go-round now move if the kid walks in 1 meter? Any guesses before we do the math? 2. Okay. Why did you say 2? Okay. So he moves in half the distance. He doubles the angular velocity of the merry-go-round. Initially, that's probably the answer most people either didn't want to say or would come to. Okay. However, it's not actually going to be the right one because we have to account for the fact that the merry-go-round itself doesn't change. The merry-go-round itself is static in terms of its rotational inertia throughout the problem. So we have L of the kid plus L of the merry-go-round equals L of the kid final plus L of the merry-go-round final. Now the kid is a point on this merry-go-round, so we can treat him just like we treated the comet, where he's going to have mr squared omega. And the merry-go-round itself, we said we could treat it as a disk, where the rotational inertia for a disk is half mr squared. Test, you'll have those on a table so that you can actually see them. You don't need to memorize those. Times omega. Initial, 1. And this will be equal to mr2 squared omega final plus half mr squared omega final. Now I do want to point out, initially they're both rotating at the same rate, and at the end they're still rotating at the same rate. So these are going to have a common variable. Plugging in numbers, I have 94 times 2 squared times omega, which is 1, plus 1/2 200 times 2 squared times 1 is equal to, kid's mass didn't change, 94, but his radius did, 1 squared omega final, plus 1/2 200. Radius of the merry-go-round didn't change, 2 squared omega final. Questions about plugging numbers into this? Okay, so I've got 4 times 94, or 384, plus 400 is equal to 94 omega f plus 100, 400 omega f. Simplifying, 784 equals 494 omega f. Divide, and I've got my answer. 784 divided by 494 tells me that it's now rotating at 1.59 radians per second. So it did increase, but it didn't double because the merry-go-round itself didn't change. If you're standing on a merry-go-round, are you going around the circle at the same rate that the thing you're standing on is going? Yeah. I mean, unless you start like walking in the opposite, like counterclockwise as it's rotating clockwise, which is an entirely different problem. Other questions pertaining to this? Okay, so tomorrow I'm going to have a worksheet entirely dedicated to these problems and working with conservation of angular momentum. Today, I wanted to give you guys the opportunity to ask any questions about the sim from last week or finish it if need be. If you are done, great, make sure to turn in. If you're not done, do that.